Onboard XPoSat, which Ashwin just now mentioned. So, I will be mainly focusing on how we designed the POLIX instrument. So, POLIX stands for Indian X-ray Polarimeter, and the XPoSat stands for Polarimeter Satellite. So, Professor Biswajit Paul is the PI for this instrument. Now, so far only 2 X-ray polarimeters have been flown. So, first one is IXPE, which is flown on 21st December 21, which is by NASA, and the second one is from India, which is flown on 1st January 24 by ISRO. So, the IXPE works from 2 to 8 keV energy, and our POLIX works from 8 to 30 keV energy band. So, both are used for studying polarization, which is degree and angle of polarization of celestial X-ray sources in different energy bands, and they provide information about the X-ray sources. POLIX is an unique instrument with proportional counter based detectors and a rotating satellite while observing X-ray sources. This is the uniqueness of the POLIX instrument. So, in this is the entire satellite. So, this is the POLIX instrument, and this is the XPECT instrument. XPECT is designed by ISRO and POLIX is from RRI, and this is the entire satellite bus. It's not working. So, XPECT stands for X-ray Polarimeter, which is from Space Astronomy Group of ISRO. So, we have already seen this. So, where we observe is over here, this is the 8 to 30 keV band here. Okay. So, our instrument observes in this energy band. So, this is an example. So, where the AM radio, FM radio, microwave, they were all in the higher frequency side, and in the higher they are in the lower frequency side. In the higher frequency side we have X-ray, and even human beings will be emitting the infrared waves, which we can see through the night goggles. You would have seen in the movies people watching, in the night time how people are moving out. So, that is one example for infrared, and for visible light, the light bulb is the one of the example. So, now why we have to go to space for studying the X-rays? This is because X-rays are absorbed by the Earth's atmosphere. So, because of that we have to put our satellites above, about some 200 to 300 kilometer above our Earth's atmosphere. So, visible light reaches Earth, and some of the infrared, infrared also does not reach, but radio waves will be reaching to the Earth. So, this was designed in collaboration with ISRO, is completely developed at RRI, and we will be discussing different aspects of this design. So, this is an instrument to measure the polarization of X-rays from celestial sources, which I already mentioned, and this measures degree of polarization, means how many photons which we receive are polarized, and the angle of polarization, what is the angle of the polarization incoming signal. And this studies helps the scientists to understand orientation and strength of magnetic fields in sources, emission processes in sources, geometry of sources. So, now let us see what is the principle of operation. This instrument is based on anisotropic Thomson scattering of X-ray photons. When the X-ray photons are coming and falling on a scatterer, they will get scattered. Photons from the sources are made to fall on a low atomic mass scatterer. In our case, it is a beryllium. And in this scattering, there is a larger probability of photons to be scattered in a direction perpendicular to the direction of electric field vector of the incoming photon. Here you see azimuthal modulation from polarized sources. If it is a polarized photons coming, then we will see a modulation in the photon count. If modulation is not there, then it is a uniform count rate with unpolarized source. So, this is on the rotating platform. There will be 4 detectors, which we will see later. So, this is the detector configuration. There are 4 detectors are there in our POLIX. So, in here you see there are one detector has been removed so that you can see the inside, and in this detector the top plate has been removed so that you can see the wires here. There are totally 12 wires, they are grouped as 6 plus 6 wires. So, each 6 wires will have the complete processing electronics chain associated with it, and there is a scatterer which scatters the incoming photon, and there is a collimator which restricts the field of view of the instrument to 3 degree by 3 degree. So, this is the complete mechanical configuration. It consists of a scatterer which we have seen in the previous one. So, this is the scatterer, sorry. The scatterer is facing the source. 4 detectors are placed in a cyclic symmetrically to cover all sides of the scattering element. A collimator which will be restricting the field of view. The configuration will be rotated about the weaving axis. So, this is another inside picture, you can see how it is arranged. And these are the few specifications. So, photon collection area is 640 centimeter square, energy range is 8 to 30 keV, and detectors are position sensitive proportional counters, and total weight of the payload is 130 kgs, and the overall dimension of the 4 detectors is 650 by 650 by 600 mm cube. It is excluding the electronics part for the digital signal processing, and total power is about 80 watts. And the data generation rate is 6.5 gigabits per day, and the scattering element used is beryllium, and the lifetime is 5 years for this instrument. So, this is the instrument configuration. You can see the detectors over here. This is 1, 2, 3, 4 detectors, and this is a collimator, and the detectors have the front end electronics right next to them, and there is a processing electronics. They are sitting slightly away from that to process the signals from the 4 detectors. We will see them in details later. So, this is one another complete zoomed in image. You can see the processing the front end electronics sitting here, and the detectors are 4 detectors, collimator, and this is one of the detector removed inside view. So, now how this was constructed we will see. So, this is constructed on the aluminum what you call completely aluminum things which have been machined out. So, they are position sensitive multi-wire proportional counters. 4 such detectors are used to cover all sides of the scatterer. So, this is one of the detector. Here you will see the big bushes here. There are 12 such bushes, and they will be having anode wires. So, and the entire detector is filled with xenon gas at 800 torr. So, this is the wire frame, and this is a zoomed in version of the wire frame. What you see here is each cell has the cathode wires, and in the center there is an anode wire. And in total there are 12 anode wires, 30 anti-anode wires, 350 cathode wires. In total 396 wires have been wired here. So, this is the collimator, so which helps us to restrict the field of view to 3 degree by 3 degree, and there are totally 757 hexagonal tapered holes are made in this aluminum block. And this is the scatterer which scatters the incoming photons when it falls here. So, this is the scatterer which is made of beryllium, and this is been fixed on the aluminum folder. This also is used as the base plate. So, for polarization measurement we need to find the azimuthal distribution of photons falling on the detectors. So, sorry. So, the incoming photon falls on the scatterer, this will get scattered perpendicular to the incoming photon, and while taking one reference direction we can find out which direction they have received in the detectors, because these detectors are rotating and it's rotating on the X-ray, the complete rotating on the satellite, it is on a rotating platform. So, the primary requirement of electronics is to determine the detector and the wire in which the X-ray photon has finally impinged on. So, this complete electronics has been divided into 5 different parts: front end electronics, processing electronics, common electronics, housekeeping and TMTC. So, we will briefly describe this in the next slides. So, this is the complete block diagram of our POLIX system. As we have mentioned, there are 4 detectors, and all the 4 detectors have associated front end electronics, because as soon as we receive the X-ray photons, it will get converted into charges, and those charges, without any noise related interference, they have to be amplified. Because of that, we have put the front end electronics right behind the detector pockets itself. And once the charges gets converted into voltage, they will be sent to the processing electronics. There we have the analog to digital converters, and further processing takes place in the processing electronics. And there are 4 detectors, and there are 4 processing electronic setups are there. So, from all these 4 detectors, the signals needs to be combined, and for that we have one common electronics. So, it will take data from all the 4 detectors, it will combine it and then send it to the satellite bus. Here there is only one system, one common card we have. In case there is any problem with one of the this card, then the entire mission becomes useless. So, for that reason we have a redundancy here. There will be 2 cards here. So, the signals are connected to both the cards, but only one card will be on at a time. If you find any problem, let us say there is one of the card has been failed, we can immediately switch over to the other card and continue with our instrument. And likewise, we have to figure out the health of the system, the health parameters of the entire system also has to be monitored. For that we have housekeeping system. So, housekeeping system will have ADCs for measuring different voltage levels and threshold settings, and it will be sending to a TMTC payload card. From the TMTC payload card, it will be sent to a 1553B card, and then it will go to the satellite bus. Here also there are 2 such cards are used, because if one card fails, the other card will take over. The commands also will be sent through the TMTC cards. So, now let us see how we will be identifying on which of the wire the X-ray photon has fallen. So, this principle is called as charge division. As we were saying, there are 6 wires. Let us say one of the photon has impinged on here, and this will develop the charges. These wires are resistive wires. So, this when it hits over here, this will develop charge. So, here in this place, because the length is lesser, we will receive more charge here, and here the length is more, here we will receive less charge here. So, when we convert this into voltage, this we call it as P1 and this we call it as P2. So, this is for peak 1, here peak 2, because the signal has the photon has fallen here, there are more charge in this, because of that the peak is more here, and this it has to travel for longer distance, this smaller peak here, to know the length from here to here. So, where it has fallen, this is the unknown length, but the total length is known. So, to find out the unknown length, you have to divide this by P2 by P1 plus P2 and multiply by the total length, we will know where the X-ray photon has fallen. So, this is the main principle which is used in this detector. So, this is another zoomed in version, the complete version of the picture. Here are the 4 detectors, and the associated the front end electronics are sitting next to, in each of the detector pockets, and the digital electronics things are sitting over here. There are 2 types of cards, one is type 1, other one is type 2. In type 1 we have a common electronics card, in type 2 we have TMTC related cards also, which will help us to take the data from the instrument to the satellite bus. So, now we will see some of the the history of these cards. So, initially we started with the lab version. So, then the lab version cards were made with the locally available components. So, you can see this is our first version of the front end electronics cards, and these are the first version of the digital electronics cards, where the processing electronics, common electronics and the housekeeping electronics, all cards are been made, and we have tested it initially. So, this is the zoomed in version of the individual those cards. and this is how we package and test inside in our labs. So, this is the complete package in the space qualified version. Space qualified version means all the components have to work in the space which goes through the different temperatures like minus 25 degree to plus 55 degree temperature it has to withstand. All those components were used and this entire system was made. Here you can see there are the back end the BE packages 1, 2, 3 and another one is the back side, and there are these are the 4 detectors, this is a collimator, everything is as a space qualified model has been made, and even the wires also have to be made using the space qualified wires. The complete harness assembly everything was been made, and this space qualified version was made by a ISRO certified vendor in Bangalore, that is called Centum Electronics, which is in Yelahanka. We did the basic design of everything and also all testings were done at the lab at RRI. So, these are the different cards which we made for the space qualified version or the final system. This is the front end cards here. So, you can see here this is a high voltage generating card and this is a high volt HV control card, this is a CSPA card, this is a HV distribution card, this is a power card for this is for the command interface. And the main digital cards were there, P analog card, digital card, then housekeeping card, common electronics, TMTC, payload card, TMTC, RT card. These cards are back end cards, these are front end cards. So, when we go for the space qualified system, we have to go at different steps. One was the lab model, the second model was the qualification model. In the qualification model, all the different temperature and the vibration related things needs to be tested for the system. So, if it is working fine with the different temperatures, then only these systems will be qualified. Here we will use the space qualified components and make the system and check it and make sure that everything is working. Once everything is working, then only we will be making the space qualified FM model or flight model. So, this is in the lab how we have started assembling and testing. So, this is the QM complete test setup here. When we are testing in the lab, we use handle the radioactive sources to make sure that the X-ray photons have been detected by the detector. So, this is the again lab test setup. This is for the complete system. You can see there are 4 BE boxes and only one detector. Initially, we connected one detector with each of the back end boxes and made sure that everything is working fine. So, this is another view of the entire test setup. So, this is the FM lab tests, and once we do all the lab tests, we have to take this system to ISRO and make sure that all the other tests which are needed to be conducted before it is flown to be done. So, this EMI, EMC, thermovac and this our system needs to be integrated with the satellite and the test needs to be done, and once this test is done, then we have to make sure that the entire satellite has been assembled and the further tests have to be done. That is called as IST pre-shipment. That means before it moves to Sriharikota. Sriharikota is a spaceport of India. Before it moves from Bangalore, we have to test the entire thing here. That is why it is called as integrated satellite pre-shipment test. Once this is working, then we are ready for launching the system. And during all this test, data from the POLIX was verified and found to be fine. Because if you miss anything, once a satellite is launched, you cannot go up and fix the system. So, make sure that all tests are done, everything is working fine. So, this is some of the tests which we did at ISRO. This is the thermovac chamber. So, all 4 detectors and our back end boxes, everything has been being put into the thermovac chamber, and all the tests were done over here. So, this is one of the another view, another zoomed in view of the same chamber. So, this is connection being done and tests are going on. So, this is again some more tests were done. At that time a photo was taken. This is for the vibration test. So, this is EMI EMC test being done at ISRO, and this is a complete system. So, all 4 backends and 4 detectors are here, and this has to be, as we are mentioning, this has to be integrated with the satellite. This is a solar panel, this is our POLIX being integrated on the satellite bus. You can see this is the complete satellite bus and this is the POLIX. So, this is the XPoSat configuration, these are the solar panels, this is the POLIX, this is the back end electronics, and this is the X-ray spectrometer from ISRO. So, this launch took place on 1st January 2024 at Sriharikota, and the orbit is low Earth orbit, altitude is about 650 kilometer and inclination is 6 degree, and orbital period is 97.7 minutes, number of orbits per day is 14.7. So, that is all. Thank you.